I'd like to talk to you a bit about how we've used Java in programming our robot this year. Oops. So here's a picture of our team wearing appropriate attire, and there you can see this year's robot, and we were fortunate enough to win one of the regional competitions this year with that robot. How many of you here have any experience of the first robotics competition? Okay, some of you, great. So for those that don't, then I'll do a little bit of explanation. First Robotics is a program for high school age students, and it brings mentors from all different kinds of backgrounds, but primarily focused on technology, into student teams, and each year you have 6 weeks to build a robot. And this is not like a little tiny Lego robot. This is a big robot that can weigh up to 120 pounds. So they're trying to create real situations where you have too much to do in too little time with too little money, and all kinds of other constraints. And then you compete with your robot. And this is not a BattleBots type thing. It is a contact sport as far as the robots are concerned, but there are a lot of rules about that contact, and you're not out there to try and destroy the other robots. You're out there to try and win the game. This year's game was essentially a basketball game, played with a few little twists to it. So it's played with 8-inch foam balls rather than actual basketballs, and there are actually 4 hoops at each end of the field. And it's played on a field which is about the same size as a basketball field, tennis court, that kind of size. There are obviously a lot of rules, and exactly what the game is changes every single year. So you don't know until like the first weekend of January what the game is going to be, and you then have 6 weeks, technically about 6.5 weeks, to build your robot and seal it up in a big plastic bag, and then take it off to compete. The plastic bag thing is all about giving people the same amount of time to actually build and work on their robot, regardless of exactly when your regional competition is. So robots must weigh less than 120 pounds. By the time you put a battery inside the robot and added some bumpers, that makes the thing weigh close to about 150 pounds, which I think is the OSHA limit for a 2-person lift. So I think that's one of the reasons why they chose 120 pounds. And it must fit in a box, and they actually check this at the tournament. At the start of the match, it has to fit inside a box that's 38 by 28 by 60 inches. So the robot can be like this tall. And the match is played 3 robots against 3, and I'll show you a short video a little bit later, just so that you can see. And each match is 2.25 minutes long. The first 15 seconds of that, the robots are all autonomous, so they're doing whatever you've programmed them to do. And then you've got 2 minutes of what they call teleoperated time. So that's where students are controlling the robots. And you normally have 2 students who are controlling different parts of the robot, another student who can actually handle the game pieces, in this case the balls. And then you have a drive coach, and that, at the discretion of the team, can either be another student or a coach/mentor. So this is kind of what the field looks like. You can see half the field here. You can see one end you've got those 4 hoops in a diamond shape there, so that you've got, you get 1 point for the bottom hoop, 2 for the middle hoops, and 3 for the top hoop. And then you've got these strange things sitting there at the halfway line. Firstly, there's a little stainless steel barrier at the halfway line of the field. That's basically 4 inches square, and it's just there to make the challenge of moving around the field a little bit harder. And then you've got these 4 bridges, or they're kind of like teeter-totters in the middle there, and they play 2 roles in the game. Firstly, they're an alternate to being able to cross over that barrier there. But obviously you need to be some way of pulling that bridge down so that you can drive up onto it if you want to cross over it. And then at the end of the game, you can get bonus points by balancing on the bridge with another robot. And with the bridge in the middle of the field is kind of unusual in that you get bonus points for balancing on that bridge with a robot from the opposite side, from the opposing alliance. And you're awarded what they call co-opetition points for doing that. And the co-opetition points play had a lot of influence this year on the seeding at the end of qualifying matches. So that's a picture of us balancing at the end of a match with one of the opposition robots. And you can see one of the foam balls down there on the floor too. So this year we made our robot drive in the backwards and forwards in the wide direction. So you want to be able to drive around and pick up these basketballs off the ground. So you want as wide a hole in the front of your robot to put balls in, to make it as easy as possible to drive over the top of balls. So we made the front of our robot the 38-inch wide part, and we had eight pneumatic wheels, which gave us enormous grip on those on the bridges and came in very, very handy for balancing with. And it also meant that we could cross over that barrier that I talked about as well. And we actually made the robot symmetric so that you could harvest from the back or the front. It just meant that the driver had to be able to drive the robot both ways around. But she got used to that pretty quickly. And we built a ball shooter that was controlled by a camera. And we had a very simple way of being able to tip the bridge down so that we could drive up onto it, or a partner robot could. And if we get time, I'll talk about some of the sensors that we used and how we used them. So onto the software. Well, the software was written in Java, and we used a library called WPI-libj to do the software that runs on the robot. And this is an open source library that's written especially for the FRC competition by Worcester Polytechnic in Massachusetts. And the Java that we're running here, it's actually the Squawk virtual machine, which is the Java that runs on the little sunspots, if you've heard of those. And we worked to port that to the PowerPC hardware that is used for the first competition. And essentially it's headless mid-P, so mid-P without the graphics. And then on the driver station, one of the things that we did for the first time this year was that not all of our software is actually running on the robot. So you have a PC-based control system that you attach joysticks and gamepads, whatever you want to use as your control devices to. And that sends basically communicates with your robot code so that the state of those control devices is communicated to your robot code 40 times a second. A new thing that we did this year, new for our team at least, was that we also ran additional code on that driver station and took advantage of the fact that you've got, compared to what you have on the robot, you've got a honking big PC sitting there, really not doing very much. And this year we used it to do image processing of a video stream. Now this was not a brand new laptop. It's a very small, it's actually smaller than this one here, that physically smaller than this one here that I'm using to present with. And it was about 3 years old when we started using it. And we, as far as we could tell, we only ever used about 20% of the CPU. So the stuff that we were doing was not actually, that complex or CPU intensive. And the robot and the field communicate using Wi-Fi. So you've got basically IP connectivity between the robot and the driver station, and they open up certain ports to allow you to do that kind of communication. So the way that WPI-lib is structured, there are really three concepts that you have to think about when you're designing your code. The first is something called a subsystem, and that's just a functional grouping of components within your robot. And I've listed out the subsystems that we had this year. The drive base, well, that's the part of the robot that actually, holds the wheels on, has the drive mechanism, the motors, the transmissions, the chains, or this year we used drive belts, saved a few pounds of weight. And we have sensors on the gearboxes so we can tell how each side of the robot is moving and so on. The ball harvester, well, that's the thing that can pick up balls off the ground, lift them up, store them until they're needed, and then deliver them into the shooter at the point when you actually want to shoot a ball. The bridge tipper, well, that's a little mechanism that just pokes out of the front of the robot so that you can drive up to a bridge and tip it down and drive onto it. The shooter I just missed out. Well, it's pretty obvious what that does. The autonomous subsystem, well, that doesn't have any sort of physical analog on the robot. It's just there to manage the selection of which autonomous program we want the robot to execute in this match. So it's kind of a virtual subsystem. So not everything that you do has to be physically related to the way the robot is. And then finally a camera subsystem. So that subsystem managed all the communication to and from the software that was running on the driver station. And basically a subsystem class, you have to extend a subsystem class that's provided by the library. But other than the fact that you extend that class, there are no requirements on a subsystem class. So you really have to think, what are the operations that I want this class to expose? Do I want to expose the ability to drive straight or go backwards or whatever? And then you can start thinking about, okay, what methods do we want to implement for this subsystem class? Another key concept is something called a button. So typically, a button essentially represents a control input to the robot, and normally then this would be a real button on a real joystick or a real gamepad, but it doesn't have to be. It could be a virtual button. So for example, if the harvester motor current has been high for more than a second, then let's consider that button is pressed. That way we can make something happen within the robot when we spot that situation occurring. And one of the goals of the way that WPILib has been set up is to try and avoid having to expose high school students who are just learning to program and just learning Java. We're trying to avoid having to expose them to multi-threading and synchronization and semaphores. And it's hard enough for them to actually be able to program without trying to explain to them exactly what the Java synchronized keyword means, and all the things that you really need to know in order to use it correctly, and so on. So, using these buttons, and buttons get mapped to things called commands, which you'll see in a moment. And they basically cause that command, the associated command, to get scheduled. Having that mapping be dynamic is actually very nice, because if you're at a practice session and the drive team tell you, oh, I really wish this button was over here, then you can say, okay, give me 2 minutes. And you can fix that. So that's a way of making the drive team very happy and very productive. Oops. So very quickly, this is what. So a command is basically a way of encapsulating an instruction to a subsystem, and there's a thing called a command group that lets you form groups of commands into something that you can schedule in one go. Now, we actually created 65 commands this year. I was really quite surprised when I went and counted them up at the end of the season. That includes a lot of debug and calibration type commands, and all of the different autonomous programs that we came up with during the season as well. Let's just go back here and take a very quick look. This is probably a bit of an eye chart for you guys. I'm sorry about that. But essentially, we created a button called a disabled only joystick button. So we wanted a button that would only be activatable when the robot is disabled. So when it's sitting there on the field before a match even starts, and you want to be able to tell the robot, I want you to run autonomous program number 3. by pressing the +1 button 3 times. So this, basically, all you have to do is implement a get method that returns whether or not the button is pressed. And you can decide what it means, what calculation you need to do in order to determine whether your button, real or virtual, is actually pressed. Obviously, if you're talking about a real joystick button, then there's code there that already does that. So you just have to instantiate the right class with the right parameters to the constructor. One of the things that helped to grow the number of commands that we had was the fact that we wanted the robot to be as functional as possible when things start to break. When a sensor wire breaks or something like that. We put a lot of emphasis on automating the software so that there's as little room for error in what the drive team does as possible. But things happen, sensors break, wires break, motors burn out, and it's important to have a manual backup and to actually train the drive team, have them practice using that manual backup system so that when something does go wrong in a real match, then you know how to deal with it. It's not scary. You don't waste the rest of the match trying to work out what happened, and you actually have a way of working around it. Okay, sorry. So a command always, always extends a class called command base. So you provide a constructor, and there is an initialize method that's called when the command is scheduled. There is an execute method that's called on about 40 times a second while the command is active. And then there is a method called isFinished, and that's called by the framework to ask the command, are you done yet? So in this case, it's a very simple command. All it has to do is essentially set a state variable in a subsystem, so it just returns true. Obviously, if your command may involve moving something until you get a certain sensor reading, then your isFinished will be a little more complex. And then there's an end method that's called once the command is complete, and then there's also an interrupted method. So commands are associated with one or more subsystems. When you schedule a new command that needs one of those subsystems, then the existing command that was using that subsystem will get interrupted. And we didn't actually have to implement any interrupted methods this year, but there is a mechanism there to deal with that. I said that we built a shooter that used the camera. Well, each of those hoops has a rectangle of retroreflective tape. That's the kind of tape that you find on children's coats or boots or whatever that reflects car headlights straight back in the driver's vision. It's incredibly directional in the way it reflects. You can be illuminating it, and if you stand a few feet off to one side, it won't look any different. The moment that you line your eye up with the light that you're illuminating it with, and you'll really see it. So we put some green LEDs around the camera lens, and made good use of the reflective properties of that tape. And so we mounted we had a fixed camera that was mounted on the shooter. The shooter could move in azimuth, so it could point in different directions relative to the robot, and it has what's effectively an elevation control, and we can also vary the wheel speed of the shooter. The shooter is basically a single wheel, and as it shoots the ball through, it puts a vast amount of backspin on the ball. I'm not a native basketball player, but even I know that backspin's a good thing when you're playing basketball. And we found that through experimentation that when you put that much backspin on there, if you hit the backboard behind the net, the ball is going in. So we found a way of getting that backspin very naturally just from the design of the one-wheeled shooter. So the camera that's on the robot is just it's actually a rather old webcam. It was probably state of the art about 4 years ago. So maximum VGA image, we actually used 320 by 240 because we found that that was enough pixels to give us the resolution that we needed to be accurate with our shooter. So the video stream that's coming from that camera goes directly to the driver station. It actually bypasses the computer on the robot entirely. The software on the driver station processes those video frames, and I'll talk more about that later. It identifies the target coordinates in each frame and sends those target coordinates back to the robot. So the robot then receives basically an X and a Y, and that's the coordinates in the camera frame of the center of the vision target. So we can use that X value. If the shooter is pointing in the right direction azimuth-wise, so left to right, then the vision target will be, quote, in the middle of the camera field of view. Now I say quote in the middle of because you never quite make that camera point directly down the center line of the robot and directly down the line where the ball is going to go when it comes out of your shooter. So that's just a parameter that you have to calibrate to say what are you going to regard as being the middle of the field of view. And then the Y value, if you think about it, the further away you are, then the lower down in the field of view the vision target will be, and that means a higher number. Y will be a higher number. And we used linear regression. We did a lot of calibration work and curve fitting, and used linear regression to basically work out for a given position on the field, distance away from the target, i.e. a given Y value in the camera, what wheel speed and what shooter elevation do you need in order to get the ball in that target, to go in the hoop. So we basically derived some fourth order polynomials that we used for that, and a little thank you to Wolfram Alpha for being so easy to use for that kind of thing. If you're not familiar with that and you do any kind of manipulating numbers, I'd highly recommend it. And we then use PID control for all of the things that you can adjust about the shooter in order to get accurate control. And so this graph here shows the polynomial that we used for converting from Y coordinate down the bottom there to the wheel speed RPM number that we needed on the Y-axis there. So you can see, and there's a separate curve going on at the same time for adjusting the elevation, and there's obviously some interaction between those, which is why this is a slightly strange shape. But you can see that as you start to get further and further away, then the RPM makes an increasing amount of difference, or you have to adjust the shooter wheel speed more and more as you get further away from the target. But using linear regression like this is nice because you're not doing sort of lookup tables, or if it's between this and this, then use this value kind of thing, which is very laborious and easy to break. And it's really a very simple computation to do, and it works really. It's a technique that we've used for several years, and it works really, really well. So azimuth control, well, so when you receive target information, then you may be on target, or the target may be to the left or to the right of center, in which case you have to move the azimuth of the shooter in order to account for that. So we have an encoder that allows us to know the position of that azimuth. So we can then convert the pixel offset that we've got from the camera picture to an encoder offset. When the encoder changes by this much when you move the camera just enough so that the target moves 1 pixel. One thing that we found that we did need to account for is the time lag involved in all this. The time lag between when the photons actually hit the sensor in the webcam to the JPEG being encoded inside the webcam, to that being transmitted back to the driver station, being processed, and then the target coordinates coming back to the robot, and you then actually controlling the mechanism to do something. So we kept, we called it an Azimuth history, so that we could, when we received new data from the camera, we could actually look back in that history to see where was the azimuth pointing, and we used the number 200 milliseconds. Where were we pointing 200 milliseconds ago? And that's the number that we need to use the offset from the camera on in order to work out where we really need to be pointing now. So once we got the time lag thing worked out and the azimuth history working nicely, then we found that even when the robot was driving around, the PID loop for the azimuth control converged very, very quickly, and you could drive past the target and watch the shooter actually follow really quite accurately as you were driving. So this is what a camera image looks like. The observant folks among you will tell me that doesn't look like, that those don't look very green. Yes, this was taken using blue LEDs. But you can see the way in which the vision targets are reflecting the incoming light. So in the driver station software, then we convert the image to HSV. And then we apply a color threshold so that we turn the 24-bit image down into a 1-bit binary image, which we can then further process. So we were using a Google code project called Java CV, which is basically a Java interface to the OpenCV image processing package. And ran into an interesting issue with one of the thresholding functions in there, which basically wouldn't let you have a threshold of. There was no way of specifying a threshold of 256, and it only applied a less than to the upper threshold, which meant that if your image was kind of overexposed or well saturated, you actually missed a lot of pixels out of your thresholding. So we ended up having to jump through some hoops and basically process each of the HS and V channels separately, and then kind of AND them back together to get the final binary image, rather than using the function that you ought to have been able to use to do this in OpenCV. I think that's actually been fixed, at least in the C++ API for OpenCV. I think that's now been fixed. But it tripped us up for a while until we realized what was happening. So as you can see, this is the thresholded image. And the threshold has been tuned, and we continue to tune the thresholds over the course of the season for different lighting conditions and so on. But you can see that there are sort of gaps in it. And if you look at that top one there, you can, at the bottom of the top rectangle there, you can really see where the hoop and the net kind of get in the way and make a nice hole, make that rectangle non-continuous for you. So we then use what's called a close operation on that image, which basically means that you kind of spread out the white area, which will tend to close up small gaps, and then you selectively erode that back so that you get an image that's more like what you started with, only with some of the gaps closed up. And you're basically counting the number of white pixels, white neighbors that a pixel has, in order to determine whether you should keep it as white or turn it to black when you're eroding it again at the end. And we deal with the rest of the gaps. So this is the same image after it's been dilated and then eroded. And you can see that most of the gaps are gone, but not all of them. So we still had to do a little more work a bit later in the process too. So what we then do is contour detection. So this gives us a very complex set of contours, which you then approximate, get OpenCV to approximate those contours down to a resolution that will allow you to tell, is this thing does this thing look a bit like a rectangle or not? So we convert we approximate those and convert them to polygons basically, which we can then work with. And in order to deal with the remaining gaps, we do some heuristic at this point, where we're approximating the outline of that polygon in order to complete broken outlines. And essentially, when we get to the stage of having a set of polygons that are candidate targets, we then say, well, we know what kind of thing we're looking for, so we know something about how big or little it ought to be in the field of view. So if the area of the polygon is less than a certain amount or bigger than a certain amount, then we're going to, you're not the target we're looking for. You really ought to have 4 corners if you're a rectangle. And the angles between your corners ought to be, roughly 90 degrees. Now, obviously, with perspective, that will change, so it's not exact, but you can still put some limits there and again, get rid of some more false positives. And we also know that we're looking at a rectangle with a specific aspect ratio, and we know kind of, based on where we can be on the field, how much that aspect ratio can seem to change when we look at it. So again, you can put more heuristics in to allow you to select the right target and not get confused by false positives. And then finally, so this is basically an image that's marked up with the final rectangles that we spotted. And you'll see that we've got a nice set of eight rectangles here, 4 of which are contained within the other 4. So obviously you throw out any rectangles that are contained within one of the other rectangles that you found. And that way you're only looking at the outside edge of the tape rather than the inside edge of the tape. Now, this is what the drivers actually see on their driver station screen. So they can see that they get a nice visual indication that the targeting system is actually working, and that communication with the camera is good, and so on. So all of the targets that are seen get highlighted in yellow, and the one that the driver has actually told the robot, that's the one I want you to aim for, is highlighted in red. So they can then, now there's no way, you may not always see all of the targets, of course. So there might be a robot in the way, or you may not be looking at all the targets because some of them are outside of the field of view. So there's no real way to say, always go for the one that's in the middle and on the left. Really all you can do is say, go for the leftmost one that you can see. So in that case then, obviously the purpose of this display was to give the drive team a visual confirmation, if they needed it, that that what the robot thought they were targeting was the hoop that they think they're aiming for. So this is kind of we actually capture quite a lot of images and store them on the driver station during matches, so that we can continue to debug. And when the drive team comes along and says, halfway through that match, we were right there and it didn't shoot, then we can go take a look at the images and try and see what happened, whether it was an image processing problem or something else that was happening on the robot. So this is a slightly blurry image because it was taken while they were driving away from the goal, having just scored. So most of the time then all the time wherever possible, we run our shooter in what we call automatic mode. And the fire button that the student is pressing is really a permission to fire, or fire when ready button. And the robot will actually shoot the ball when it thinks that the shooter's on target. So that means that the shooter's pointing the right direction, that the elevation is correct, and the wheel speed is correct, based on the camera information that we have. We can see the targets from further away than we can actually shoot, particularly when it comes to that top goal. So we also put some limits on that the Y coordinate, and then we also want the robot to be more or less stationary. And this was something that we didn't really experiment too much with. We have encoders on the drive base, so we can tell whether the robot's moving or not. But we didn't get as far as wanting to do the extra computation to take account of robot motion when we're trying to work out how to shoot the ball. Maybe an off-season project. Okay, let me see if I can play some match video. Okay. I'm guessing that QuickTime is not set up on this laptop, so maybe we won't be able to use that.
You can right-click on it, open with, and choose the player.
Doesn't look promising. Oh well. So suffice to say that doing all this in Java worked really well for us. It enabled the students to be surprisingly productive. And excuse me. We had a very enjoyable and very good season, and we had we found that offloading all that processing from the robot to the driver station really helped us do well. Any questions so far? Yes, sir.
You mentioned that you use Sunspots and Squash operating system, and you also mentioned that you had a laptop on top of the robot.
No, so that the Sunspot reference, the virtual machine that we're using on the robot is the same. It's the same virtual machine that runs on the Sunspot. We weren't actually using any Sunspot devices. So that there's an embedded controller that's donated by National Instruments that sits on the robot. That's PowerPC based. So that controls the robot, and then there is a laptop which the drive team who are actually controlling the robot, that's sitting right in front of them.
But you basically had it in the color Java SE when you had a laptop on top.
Yes. Yeah, we were.
To use the Sunspots having it in Squash, but to use the Squash is used for running multiple templates for Java and E.
Yeah. So the Squawk VM was a good choice for the actual robot controller because it's a fairly limited PowerPC based piece of hardware, and SE embedded is not available for that hardware. So for writing robot code, then robot control code, then it's fine. Obviously, having full SE on the laptop was very nice. Yes. No, we never experienced anything that I would put down to a garbage collection cycle. Clearly, you can write Java code to generate more garbage or less garbage. We made a conscious effort to do all of our explicit object allocation or explicit object usage in at initialization time. And obviously there's a certain amount of garbage that you can't help producing just because you're running Java code. But we never experience, and you've only got to. The good thing about this is that you don't have to make this lot run for days or weeks without a garbage collection. It really only has to run for a few minutes without any significant garbage collection going on.
Recently on a conference I did about robotics, all the robots were written in C. And when I asked them why don't you try Java, they said everything has to be in real time. We might have experience issues, but that will probably more complex robots. So.
Maybe. I mean, this was we we generated about 7,000 lines of Java code this season. So it's a non-trivial application. Yes?
So what was the robot program in the autonomous period?
So we had a variety of things for autonomous, ranging from, so the robot can start with 2 balls inside it at the beginning of autonomous. So obviously one of the things that you'd like to do in autonomous is to actually score those balls, because you get double the points. Actually you get a 3-point bonus for each ball that you score during the autonomous period. There are also balls, let me just go back to okay. You can see, this is actually a picture of just after a match has started, and you can see that there are some balls sitting on top of those bridges. The red bridge at the bottom left corner of the screen belongs to us with the Red Alliance, and the Blue Alliance is not allowed to touch that bridge. We can't touch the blue bridge, but the middle bridge there, we can compete for that. So in this particular instance, then our robot has deployed its bridge tipper. You can kind of see something poking out the front of it, and is heading for that bridge to go and get those other balls, so that we can then try and score those balls in autonomous and deny them to the opposition, as well as scoring the 2 that we actually start off the match with. So we had a variety of programs that would go there, or we had a program that would come to the ramp, the bridge at the bottom of the screen, and tip that to get the balls off, and so on. So we had probably about 5 or so programs that we used regularly during the season. Okay, 2 minutes to go.
Maybe I missed it, but you were determining the range to the hoop. Were you just determining by the size of the rectangle? Or
No, we actually didn't worry about the size. We just went by the y coordinate of the center of the rectangle that we found. Because as you walk closer to it, then it's going to go up in the field of view of the camera. Now, the way the coordinate system works, then that means that y is going down. So y less means you're closer, y increases as you come further away. Okay, and you don't actually need to calculate how far away you are. You just need something that's a proxy for that distance. We were running the camera at 20 frames a second. So from the point of view of the drive team, then you basically get video on screen, live video from the robot with the annotation and with the overlay added to it. No, that we found I think we did actually measure the time it takes to process each frame. It was on the order of about 12 or 15 milliseconds, I think.
So basically, in order to process faster, you use lower resolution images, so the process will respond.
We used a lower resolution image, so primarily because we were concerned about the bandwidth on a competition field, and we had no way. We knew that using less bandwidth was better than using more, and we had no way of testing that outside of competition. So we went for the lowest resolution that we could use that gave us enough resolution to be accurate in targeting. Okay, well, thank you all very much for coming.